In the last segment, we were talking about the general state of stress at a given point. If you remember, we suppose there is a generic body like that, and if we are talking about a point P somewhere inside the body. So this is a sort of 3D body as we generally draw. Like that, and P is somewhere inside the body, and when we say the state of stress at point P, what we mean is we are thinking of first let's say we have to define a particular coordinate system. Without that coordinate system we can't even talk about directions. So then what we do is we take a small cube around that thing like that, an infinitesimal cube around P, and then on the surfaces of those of that cube, and we define the stresses, and those stresses we generally represent as say in the matrix form. If we want to write, we write say sigma xx, sigma yy, sigma zz, and the other things we write them as say tau xy, tau xz, and tau yz, and their symmetric counterparts here. It's tau yx, here it's tau zx, and it's tau zy. Okay, so this is how we defined the stress tensor, or the components of the stress tensor basically are represented in this matrix form, and we also said that, or in fact proved that we don't require these 9 components separately, only these 6, this diagonal 3 and off diagonal 3, any 3, either the green ones or the orange one you can take. So that should give us the complete information about the stress that is existing at a point P. Now, but here you should make a point that, see, everything happened as we chose a coordinate system, okay, and with respect to that coordinate system we created this cube, and with respect to that cube these numbers came, okay, because these are all numbers. But then if somebody chooses a different coordinate system, obviously these numbers will change, and so there comes the confusion of when to say that a system is safe, unsafe, because we have discussed earlier that the stresses are the things or the parameters which basically define whether a system is safe or unsafe, right? Not the force but the stress. But then we are seeing that these numbers are keep on changing as soon as we move this coordinate system around. Now then which coordinate system should we choose to represent, and so that we can actually tell whether the system is safe or unsafe under a given loading condition. And then does it mean that this whether a system is safe or unsafe, it depends on the coordinate system that I choose? Obviously it should not be the case. So what it means is these numbers will keep on changing based on the coordinate system, and we will have to see that in which coordinate system some value is going to its maximum, some value is going to its minimum, and those maximum and minimum values whether they are safe or unsafe. So that's the main way to decide whether a body or a system is safe or not safe. But then there is another way, so this is one way when I said that you change the coordinate systems, you keep on changing and see how these components are moving around or changing around. Or else another viewpoint is this cuboid basically, which we picked around this point P, that we are rotating, okay, and we keep on rotating that cube and we see the stresses which are moving on that. So these two concepts are exactly the same. Either you think in terms of moving the coordinate system, or you think in terms of rotating the cuboid on which you are actually looking at the stresses. Now, so whatever is comfortable to you, you can think in that way, okay. But the idea should be clear. So that in whatever direction the values are coming to be maximum, those maximum values are of concern, okay. In a particular direction, if all the values are looking great, they are looking very safe. Suppose all the values are below the maximum stress which a material can withstand, so we cannot be very happy that okay, so everything is looking good, so the body will be safe. We can't tell that. So we have to look by changing either the coordinate system or changing the cuboid. Both are same in a way, okay. But then how to do that? Is there, so let's develop the mathematics and a particular trick, basically a tool which you can use to do this analysis of moving around the coordinate system or moving around the cuboid, and then see what's happening with these values of these stresses. But in 3D, to do that, it's a bit clumsy. So what we will do is we will not consider this full complexity of the 3D state of stress. We will consider the condition or the situation where anything related to Z is 0. Means anywhere you see, you know, the Z as a coordinate or a subscript, you just make them 0. Okay. Yep. Yeah. So they all these things have actually gone. So we are left with this many, right? Tau xx, sigma xx, sigma yy, tau xy and tau yx, which are anyway symmetric. So there are 3 values which we are now concerned with, and that kind of condition or a situation has a name. It's called the condition of plane stress. Okay. So that means such situation arise when you have, you know, say suppose a body is there and it is such that its thickness is very small as compared to the other dimensions. This thickness is very small, and all the forces which are acting on the body, they act just parallel to that or perpendicular to this thickness, you can say, or in the plane of this body, okay. So like that, suppose, okay. So these are and they are uniform across these things. And in fact, the boundary conditions which are existing, so they are also happening only in this suppose or here, if I make it fixed for some region. So anything happens that happens in this small thickness of the body, and then the stress that prevails inside this body will be of this type when we actually take the xy in some direction. Okay, so this is x and this is y, and the z is coming out of this plane, okay, of the body. So, and that is why nothing happens in the direction of z, that means no change happens. So, we can safely delete these things from our discussion, and we are concerned only with this. And once we have this, if you remember the stress cube which we were drawing, now it will become okay, I'll go to the next maybe. So, it will become just a square like that, okay, on which the stresses I will show say as sigma x and sigma y, and similarly here sigma x, sigma y, and then you have your shear stresses tau xy, tau yx, similarly tau xy and tau yx, and in fact your point P is at the center of this. So, this is the representative stress field, you can say. Instead of a cube, now we are completely we can describe the state of stress with a square. So, that is the idea. Now, so this is what, and then I will write for completeness here. So, we have only sigma xx, sigma yy and tau xy and tau yx. That is it. So, this is our state of stress. But then what we are looking forward to is that if we change this cube, which is now in fact, or this square at some by some angle, then how these stresses actually change. That means just imagine that this is a square inside a big body. Say suppose this is the body which is having a small thickness inside the into the blackboard, very small thickness, and we have this square sitting somewhere here, okay, and the x axis we have defined as this and y axis we have defined like this. But then suppose we know these stresses somehow. Now, how we can get it? When I say somehow, there is a method. For example, there are something called strain gauges which you can put on this body to measure some strains, and from that you can calculate the stresses. So, it's simple like this. Just imagine that what they do is just think that you attach a spring here, you attach a spring here, okay, to the body. These springs are attached to the body to this point P, I mean they are very small, okay, and there is another spring which is attached here, and we know the spring constants of that spring anyway, okay. Now, when you apply the stresses to or the force or all these external loadings, whenever you apply them and when you have the boundary conditions like that, something like this, wherever, and then at every point there will be some deformation, right. So, now based on the deformation which is existing at this, though I have drawn these springs too big, in fact they are just around the point P, they are very small. I have just exaggerated a bit so that you will be able to see it, visualize it. But then what you are doing is you are measuring these strains in these springs, and suppose this I'll call them say A, B and C springs. So and then this configuration has got a name, it's called a strain rosette. Okay, so strain gauge rosette. Okay, it's like a rose, you know, so that's how the name rosette. So strain gauge rosettes, if you apply, they are not these springs but very similar to these things. Okay, so they are very small things which you can actually glue it to the body, and then you can take the measurements. They'll come in the form of voltages, and the voltages are converted into strains and all those things. Whatever. For us it is the springs, and then from the spring you calculate the strains in the spring, you know, the change in length of the spring to the original length of the spring, and that suppose gives us, you know, say epsilon A, epsilon B and epsilon say C. So these are the three values of which we have got the strains from there, and suppose we know these angles, you know, theta, generally they are put at 45 degrees, okay, theta 1, theta 2, etc. So then what you can, they have developed a relationship, for example like this. I'll shift it around, right? So yeah, so then what I can do is, so it's like this, and you can directly get your epsilon x, epsilon y and your gamma xy basically from these equations, and they are functions of basically these thetas, like, you know, cos theta, this is A, so cos theta, cos theta, cos square theta A, sine square of theta A, then sine theta A, cosine theta A sort of thing, and similarly it's cos square of theta B, sine square of theta B, and sine theta B, cos theta B, etc. And similarly here, okay, I'll just write it, theta C, sine square theta C, sine theta C, cosine of theta C. So once you plug these things in, and then these thetas are measured from the x-axis and all. So and so what we know from the measurement are these things. This vector we know, all this matrix we know, so just invert this and multiply this to get this. So once you know this, last segment we saw that how to get, you know, epsilon x, epsilon y and gamma xy, how they were related to the stresses, right? Again I need some space here, let me try here, say it was 1 minus nu 0 minus nu 1 0 0 0 2 times 1 plus nu. Okay, now that times sigma x, sigma y and tau xy. Basically this is the thing. Okay, now from here, once you know this, you can always calculate this by inverting this and multiplying it here, right? So that means you are in a position to calculate sigma x, sigma y, tau xy by putting these springs at any location that you wish for. But the thing is, then you can think, you can always tell that, okay, I'll put these things and then I'll measure the stresses, and then what is the problem? The problem is you will have to again remove this from the glue and all, and you have to apply, put that thing in different direction. So you have to keep that thing or rotating these rosettes for all the angles which you require, and then out of all those values you will look for what is the most dangerous value for you, okay, which is the most unsafe value for you, and then you can do that. But it's a very clumsy idea to, it's very, you have to do it multiple of time, right? So remove it, change it, the orientation, put it, measure it, again do that, and then it's bad. So instead of that, what can be done is we will develop a mathematical technique by which just one measurement will do. Okay, you do one measurement, you get these values, and then mathematically you calculate in any direction what will be its value. So that is called the transformation of the stresses at different angles when you rotate these things at different angles. So again I am repeating, either you can think of this as change of coordinate system or rotation of a coordinate system or rotation of this elemental or infinitesimal square about the point P. Both the views are exactly the same, and then once we have this mathematical technique of transforming these stresses to any angle, we are done. So then we will just have to see at what angle we are getting the maximum values and if those maximum values are safe for us or not. And that the topic will be the next segment. See you in the next segment.